Right now, something unprecedented is unfolding beneath Iceland. Across the entire island, volcanic systems that have slept for centuries are stirring simultaneously. Magma reservoirs are swelling, fissures are cracking open, and scientists are watching data streams they have never seen before. What happens when an entire country built on fire begins to wake up at once? Why are Iceland's deadliest volcanoes all showing signs of life in the same decade? And is the world prepared for what may come next? This is not a forecast. This is an annual analysis of where Iceland stands geologically, and 2026 may mark a turning point that has been building for nearly 1,000 years. Iceland exists because of a rare collision of geological forces. The island sits directly atop the mid-Atlantic ridge, where the North American and Eurasian tectonic plates tear apart at roughly 2 centimeters per year. But that is only half the story. Beneath this rift lies a mantle plume, a massive upwelling of superheated rock rising from deep within the Earth. This hotspot pumps enormous volumes of magma toward the surface, feeding Iceland's 30 active volcanic systems. The result is a landmass being both pulled apart and pushed upward simultaneously. What we observe in any single year is merely a snapshot. Volcanoes operate on timescales that dwarf human memory. Seismometers record monthly microcycles, brief pulses of activity that ripple through the crust, but these short rhythms exist within far longer patterns. The Reykjanes Peninsula, for example, follows an 800 to 1,000-year cycle of awakening and dormancy. The last Reykjanes cycle ended in the 13th century. For 800 years, the peninsula slept. Then, in 2021, the fires returned. But something deeper may now be stirring. The simultaneous unrest across multiple volcanic systems raises a troubling question that scientists are only beginning to ask openly. Are we witnessing the activation of a much larger, longer-term cycle? And if so, what does that mean for the 400,000 people who call Iceland home? The story begins offshore, where Iceland's volcanic backbone first breaches the Atlantic surface. The Reykjanes Ridge extends southwest from the peninsula, a submerged continuation of the same tectonic forces that built the island. Most of this structure lies hidden beneath cold, dark water. History offers a grim reminder of what these waters can produce. In the early 19th century, a volcanic island called Geirfuglskar rose from the ridge. It became the final refuge of the great auk, a flightless seabird once abundant across the North Atlantic. Then the volcano erupted again, and Geirfuglskar vanished. The last great auks were slaughtered shortly after, their species erased from existence. The geological and biological extinctions intertwined, a parable of impermanence written in fire and feathers. Today, underwater magma systems along the Reykjanes Ridge remain active. Scientists monitor them with concern, particularly given their proximity to Keflavik International Airport, Iceland's only major gateway to the outside world. An offshore eruption could reshape coastlines and disrupt global travel overnight. But the offshore systems are not on the primary watch list for 2026. The real action lies closer to shore. The Reykjanes Peninsula has erupted 12 times since 2021, 12 separate events in just 4 years, each one tearing open the earth between the fishing town of Grindavik and the volcanic mountain Fagradalsfjall. The pattern began with what scientists called tourist eruptions, relatively small, accessible events that drew thousands of visitors to watch lava fountain against the Arctic sky. But the eruptions grew closer to civilization. They grew more destructive. In January 2024, lava approached Grindavik itself. Fissures opened within sight of homes. Buildings burned. The town was evacuated, and most residents have never returned. Beneath Svartsengi, a magma reservoir continues to swell. According to the Icelandic Meteorological Office, approximately 20 million cubic meters of magma have accumulated since the last eruption ended in August 2025. This approaches the upper threshold that typically triggers a new event. But something has changed. The rate of magma inflow is slowing. Some scientists speculate this could signal a final eruption from this particular source, a last gasp before the system exhausts itself. Others warn that tectonic stress could redistribute to nearby fissure swarms, potentially restarting the cycle in new locations. The uncertainty is profound. Nobody knows if eruption 13 will be the last, or simply the next. What scientists do know is that the Grindavik system, southeast of the current activity, has begun showing signs of its own. Ground subsidence patterns shifted in late 2024, and earthquake epicenters migrated toward Lake Kleifarvatn, a body of water that famously drained during a magnitude 6.5 earthquake in the year 2000. The Icelandic Met Office has noted with interest that the boundary between Svartsengi and Grindavik systems may not be as distinct as previously thought. Magma pathways could interconnect at depth, potentially allowing pressure to transfer between volcanic centers. This complicates predictions enormously. If the systems are linked, activity in one could trigger activity in the other. The peninsula may not be approaching the end of its cycle, it may only be beginning. For 2026, at least one more eruption on the Reykjanes Peninsula appears likely. The magma reservoir beneath Svartsengi continues to refill, and historical patterns suggest a new event could occur within months. Multiple eruptions remain possible if inflow rates accelerate. Magnitude 4 to 5 earthquakes will almost certainly accompany any new activity as stress redistributes across the fractured crust. But there is a deeper concern that experts discuss only reluctantly. A major fault runs directly beneath Reykjavik, the capital city where 2/3 of Iceland's population lives. This fault has not ruptured in modern history, but it is, in the words of one geophysicist, locked and loaded. Whether the ongoing volcanic activity could eventually trigger movement on this fault remains unknown. Scientists hesitate to speculate publicly given the political and societal implications, but the question hangs in the air like sulfur smoke. Moving northeast from Reykjanes, the volcanic rift continues through the South Iceland fracture zone. Here, the town of Hveragerði sits atop one of the most geothermally active regions in the country, its greenhouses heated by volcanic steam. This area marks a tectonic junction where multiple volcanic systems converge. Stress transferred from the Reykjanes activity could theoretically propagate eastward, though no immediate danger is expected for 2026. The real attention focuses further inland, toward a volcano that has terrified Icelanders for a millennium. Hekla has earned many names: the gateway to hell, the queen of Icelandic volcanoes, the unpredictable one. Medieval Europeans believed Hekla was literally the entrance to the underworld, a place where souls descended into fire. The reputation was earned through eruptions of catastrophic violence. The 1104 event blanketed Iceland in ash and altered the climate of northern Europe for years. What makes Hekla uniquely dangerous is not its size, but its silence. Unlike most volcanoes, which produce warning earthquakes days or weeks before erupting, Hekla gives almost no notice. Historical eruptions have begun with as little as 30 minutes of precursory activity. Strain measurements suggest the volcano's magma chambers are more pressurized now than before any eruption since monitoring began. Geophysicists have warned repeatedly that Hekla could erupt at any time, yet no one can say when. For 2026, Hekla is not on the primary eruption list, but it has been on watch lists for over a decade, and each passing year without activity only increases the potential energy of the next blast. The volcano waits like a held breath. North of Hekla, the landscape shifts again. The volcanic systems of Hengil and Thingvellir stretch toward Vatnajökull Glacier, a region often misrepresented to tourists as a simple plate boundary viewpoint. The reality is far more complex. This is an intraplate system where multiple volcanic structures overlap. Thermal drone imaging has revealed new anomalies along the main highway, hotspots where underground magma chambers continue to deflate and refill in slow, rhythmic pulses. The famous Rift Valley at Thingvellir, where tourists pose between tectonic plates, is not a static feature but an active depression being slowly pulled apart. The ground subsides by millimeters each year as magma withdraws from chambers below. This system shows persistent signs of life, but poses no immediate threat for 2026. Far to the west, the Snifellsnes Peninsula tells a different story. Here, earthquake activity has increased dramatically since 2024. Seismometers detect swarms at depths of approximately 20 kilometers, suggesting magma migration through the lower crust. The question scientists cannot answer is whether this migration will continue upward. If magma reaches the 10-kilometer threshold, eruption becomes a realistic possibility. Below that depth, the material may simply stall and cool, never reaching the surface. Improved sensor technology has made detection more precise. What might have gone unnoticed a decade ago now appears clearly on monitoring networks. The data shows upward movement, slow but measurable. If Snifellsnes does erupt, it would be the first activity from this system in millennia, but competing signals from elsewhere in Iceland suggest the peninsula will not be 2026's main event. The West Iceland earthquake zone sits between systems. No eruption is expected here, partly due to statistical improbability. Iceland has never experienced 3 simultaneous active volcanic zones in recorded history. The crust can only fracture so much at once. Katla is perhaps Iceland's most anticipated volcano. For decades, scientists have warned that this subglacial giant is overdue, though the concept of volcanic tardiness is scientifically questionable. Volcanoes do not operate on human schedules. What is certain is that Katla has erupted at least 20 times since Iceland was settled, with intervals ranging from 13 to 95 years. The last major eruption occurred in 1918, meaning over a century has passed. Each year adds to the accumulated pressure. Beneath 700 meters of ice, Katla's caldera generates constant geothermal heat. The glacier above occasionally releases sudden floods as meltwater accumulates and breaks through ice dams. These Jökull have destroyed bridges and reshaped coastlines throughout history. In October 2025, a strong earthquake swarm shook the region, producing several magnitude 3+ events, but no eruption followed. Katla continues to tease, never quite crossing the threshold into full activity. For 2026, Katla remains possible but not favored. The seismic signature does not yet match the patterns that preceded historical eruptions. Beneath Vatnajökull, Europe's largest glacier, lies a supercluster of 7 interconnected volcanic systems. This is the heart of Iceland's volcanic machine, directly above the mantle plume that built the island. Bárðarbunga dominates this cluster. Its 2014 to 2015 eruption produced the largest lava flow Iceland had seen in 2 centuries, covering over 85 square kilometers with molten rock. The event lasted 6 months and released enormous quantities of sulfur dioxide that affected air quality across the country. That eruption ended, but the volcano did not rest. In January 2025, the most powerful earthquake swarm since 2014 struck the northwestern caldera. Approximately 130 earthquakes occurred, including a magnitude 5.1 event, the strongest recorded there in a decade. Seismic data confirms that magma accumulation has continued steadily since the last eruption ended. The system is reloading. An eruption beneath the glacier could produce catastrophic flooding. Meltwater would surge toward Iceland's southern coast, potentially overwhelming hydropower infrastructure and destroying agricultural land. A long dike formation, like the one that fed Holuhraun in 2014, could extend for tens of kilometers, triggering activity in neighboring systems like Grímsvötn. Nearby, Torfajökull shows unexplained ground uplift. Its relationship to Bárðarbunga remains unclear. Some scientists believe the 2 systems share deep magma pathways, while others argue they are independent. The uncertainty reflects how much remains unknown about Iceland's volcanic plumbing.
Askja volcano has risen nearly 1 meter since 2021. GPS stations record continuous uplift centered on the western edge of Askja, the caldera lake that formed during the catastrophic 1875 eruption. That event blanketed Iceland in ash, poisoned water supplies, killed livestock, and triggered one of the largest emigration waves in Icelandic history. Tephra from the eruption has been found as far away as Romania. Current modeling suggests magma is accumulating at approximately 3 kilometers depth. An estimated 44 million cubic meters have pooled beneath the surface since monitoring began. No historical measurements exist from before the 1961 eruption, so scientists cannot determine how much pressure the crust can withstand before failing. Whether Ascia will erupt in 2026 remains hotly debated among researchers. Some argue the system needs decades more accumulation. Others point to the unprecedented rate of uplift and warn that timelines may be compressing. The Reykjanes fracture zone in northern Iceland poses a different kind of threat. No volcanic eruption is expected here, but the offshore fault system is capable of producing magnitude 7 earthquakes, events that could devastate coastal communities and trigger submarine landslides. Magnitude 5 events are likely within any given year. The region experiences regular seismic swarms, reminders that Iceland's dangers extend beyond fire. Vatnajökull, the glacier covering Iceland's largest active volcano outside Vatnajökull, has revealed a new mystery. An ice cauldron has formed on the glacier's surface, indicating increased geothermal activity beneath the ice. The phenomenon is being studied urgently. All of this must be understood within a larger context. Iceland is not simply experiencing a cluster of unrelated volcanic events. The entire island appears to be entering a period of elevated activity that could persist for decades or longer. The 1783 Laki eruption offers a terrifying historical precedent. Over 8 months, the fissure expelled 15 cubic kilometers of lava, released 120 million tons of sulfur dioxide, and killed 1/5 of Iceland's population through famine and fluorine poisoning. The effect spread far beyond Iceland. A toxic haze drifted across Europe, causing respiratory illness and crop failures. The winter of 1783-1784 was among the coldest on record in the Northern Hemisphere. Some historians argue the resulting food shortages contributed to the social unrest that preceded the French Revolution. Could it happen again? The systems that produced Laki remain active. Grímsvötn, which shares a fissure system with the Laki crater row, has shown increasing signs of unrest. For 2026, Grímsvötn emerges as the primary eruption candidate. Statistical analysis of its eruption history, combined with current monitoring data, suggests activity within the next 1 to 3 years is highly probable. The question is scale. Grímsvötn typically produces moderate explosive eruptions that disrupt air travel for days, but the same system once produced Laki. If pressure continues building across multiple interconnected systems, a larger event becomes conceivable. Such an eruption would release massive quantities of sulfur dioxide, potentially triggering regional cooling and agricultural devastation across Europe. Iceland's power grid, heavily dependent on hydropower stations fed by glacial rivers, could be crippled by flooding. Tourism, which sustains a significant portion of the economy, could collapse. In the worst scenarios, parts of Iceland could become temporarily uninhabitable. Scientists do not predict this outcome, but they do not rule it out. What remains certain is that Iceland's volcanic systems do not care about human schedules, economic concerns, or geopolitical boundaries. They operate on geological time, accumulating pressure over centuries before releasing it in hours or days. Experts have issued soft warnings for years. Planning documents exist. Evacuation routes have been mapped, but true worst-case preparation remains inadequate, partly because the scenarios are so extreme that policymakers struggle to take them seriously. We are not entering 2026 with answers. We are entering with better questions, better monitoring, and better data than ever before, but the fundamental uncertainty remains. Across Iceland, magma is rising, faults are stressed, glaciers are melting from below. Something is building beneath this island of fire and ice, something that has been building for centuries. The question is not whether Iceland will erupt again. The question is which system will break first, how severe the consequences will be, and whether anyone can truly prepare for what the Earth has in store. One thing is increasingly clear. The patterns emerging across Iceland in 2025 and 2026 do not resemble anything in the modern monitoring record. Multiple systems showing simultaneous unrest, magma accumulation rates that surprise even veteran volcanologists, seismic swarms in locations that have been quiet for generations. The data does not lie, but it also does not predict. We watch, we measure, we wait, and somewhere beneath Iceland's glaciers and lava fields, forces older than human civilization continue their ancient, patient work. When they finally release, the whole world will know.